Okay, I have checked the midterm, and hopefully this week, maybe tonight or tomorrow, I will send the results. The average for your midterm is around 55 or 56. I think it's quite good. But I think there are two or three students, I think still maybe around 40 or below 40. So I think you need to study really hard. At least we have one more quiz and the final exam, and the rest will be, I think, just a homework. So I'm planning to have a quiz within this week. Maybe start from tomorrow. Okay, tomorrow, maybe until the end of the week, or maybe start from Wednesday, okay, or maybe tomorrow to Friday. And our final exam, I think we would not have on Monday. Maybe on Wednesday, or maybe the same like Friday. But I think we can have on Wednesday. I think on Wednesday. So my plan today is to continue the matrix and maybe finishing the matrix. I will just finish off until the eigenvalue matrix. Okay, eigenvalue, eigenvectors. Okay, that is the end of the matrix, and then continue to the vector calculus, which I will start with the curl and divergence, and then continue to the line integral. And if we have time, we can dive in more to surface integral and so on and so forth. So I will focus for this morning session with the matrix. Okay. Okay, but before that, let me start with some review on the matrix. That is, well, we already have the transpose. Okay, the transpose. So basically, transpose is changing the row to column, and basically saying that we are changing the shape of the matrix itself. And if we transpose and then transpose again, we will get back to the original matrix. Okay, and then this is a several property that probably we can see here. And then we have another special matrix that we are usually using it for some solutions. For some solutions, we have the upper triangular matrix, we have the lower triangular matrix, we have the diagonal matrix. The diagonal matrix is it's only half the diagonal. The other numbers are zero. Okay. The upper or lower, it's basically where your zero will be. Zero on the bottom part, it's upper triangular matrix like this picture. Okay. If you have lower triangular matrix, means that the zero will be the top part. Okay. And then you have the identity matrix, which we are going to see more in the eigenvalue later. And then we have the matrix that is symmetry. Symmetry means when we transpose, it's just as it is. It doesn't change. Okay. Okay. And then we can also make the matrix into an augmented form. We call this augmented matrix. Okay. The augmented matrix is just how we write the matrix. Okay. So usually, if we have this system of equations, this linear equation, we can write this three equation into our matrix like this. Okay, we have the 3 by 3 here, which is the constant on this system equation, and we have the variables here, and this is the right side of the equations, right? But we can make it into more simple, into a more simple form that we know with the augmented matrix. Augmented matrix, we just said that this is the constant of the system, and this is the right side of the system. Okay, and the variable is intrinsically inside this system. Okay, so we are not really writing any variables. Okay, but we know that because we have 3 by 3, we have three right side equations. So at least we have three variables in there. Okay. Okay. Now, the idea to have this matrix, if we want to solve a system equation, is the first thing is we are going to set this becoming 1. This is 1, 1, 1. So all this diagonal become 1, and all the rest here becomes 0. And this is also can be a 0 also, the above part. So we are going to make triangular matrix. Okay. Now, how do we change this into 1 and 0? Basically, we are going to need the row echelon operators. What is row echelon operators? So practically, whenever you have the augmented matrix, you can treat your matrix with each row, like we have here, are 1, 2, and 3. We can treat them as many as we want. Okay, we can treat them. We can add both of this R1, R2. We can add this together. We can treat with many operations that we want. Okay. So the idea is, if we want to change, for example, if you want to change the first part, the first row, I want to make this minus with this, so that 2 becomes 1. So let's just say we change the R1. Okay, R1 change 2 minus 1, 1, 6 minus 2, it's 4, 1 minus 1 is 2. And then 7 minus 1 is 8. So we are going to have really, right here, we are going to have really good 1-by-1 operators. Or if you confidence enough to use more than one operators in one step, that's also fine if you are able to do that. Okay? And that's good. That's good. But if you want to be more careful, you do it 1-by-1. Okay? So you have this, and then you want the second row is getting maybe this one here, maybe getting 0. So maybe the easiest part is this second row multiply either with 2, and then you can minus with the first row, or you can multiply with 5 and then subtract with the third row. Okay, and there is many ways that you can do. Okay, but the idea is to make the diagonal, making the diagonal here 1, 1, 1, and the rest here 0, or the rest here 0, or both 0, and you can get directly the result. Okay, so that's basically a row operator, and we have shown you how to do some row operators here and make it into 1, 1, 1. Okay, like this. Okay. Okay. And here also. And if we have this situation, when we have this 0, 0 on the bottom, so when we are trying to make our operations, we see these conditions. We call this is inconsistent system, and we can write there is no solution. Okay, and then the rest. And there are other things that can happen is if we have the homogeneous system. So we don't have any right equation on the right side. Means that we are going to have two categories. We are going to have the trivial solutions and non-trivial solutions. Okay, this is when usually this is also happen. These two solutions, if this matrix here, it's not only 0, 0 constant, it's 0, 0, and 0. If you have this at your bottom of your augmented matrix, it will have at least two kind of solutions. You have the trivial solutions or non-trivial solutions. So you can have infinitely many solutions. You can have infinitely many solutions. What does that mean? What that this infinite many solutions means? It means that you can have any parameters. For example, if you put t and your other variables will be having relation with those t, like this one. This one we can also call this is non-trivial solution. So if we take one variable as t, then the other one has this t also. And we can, if we take this t as 0, of course, the other variable will be 0, and that is our trivial solution. It seems that it's kind of the same as a singular solution in the differential equations, right? Okay. So that's a homogeneous system. We can also have that, and we can also solve by matrix if we want. Okay. And of course, all the system here, the matrix, it's all a linear system, And then this is some theorem, and then also we have the superpositions principle. If we have x1 or x2 as a variable, and then they are the solutions from the matrix, okay, from the matrix homogeneous system. So this is homogeneous system, and then we may have the third component or the third solutions that is involving the two variables with each constant. Okay, that's we can also have that as a solution. Okay. And after that, we learn more about the determinants, how to break down the determinants, and how about this. We have 3 by 3 determinants. What is the covectors? We already learned that. Covectors means simply we have the signs here, right? Signs. Okay. That's the covectors. And then if we have the transpose, the determinant is the same. Okay. And then there are some property of determinants. We can multiply the determinants. Okay. And if we multiply the matrix, find the determinants means we are multiplying its determinant with the other determinant. And then the triangular matrix, diagonal matrix, it's also related to determinants, right? Because of the 0, then we see that we just think on the diagonal, right? The diagonal. And then we have the row reduction. Okay, the row reduction. So this is similar to the augmented matrix, but we are just doing it with the single matrix. Okay, with this example, we have the single matrix A. Oh, before row reductions, if we interchange the row, okay, row or columns, okay, so for example here we are having the changing from this and this. Okay, we change the row, okay, and we have this. The determinant will be the minus determinant of the first matrix. Okay, the same thing if you are able to change this from the left, maybe change with the middle one, the column. You can also say that it will be the minus determinant of A if we want to find the determinant. Okay. And then row reduction, as usual, our idea is to get the 3 parts here. If you have 3 by 3, we are going to have these 3 numbers here. Our goal is to make it 0. Okay. And if we make this 0, then our determinant is just the diagonal. Okay. So it's kind of similar of what we have from the augmented matrix. The operators is the same. We can plus the rows, subtract the rows, multiply with scalars, and then subtract. Okay, divide also. All the things that you can do with the augmented matrix, you can do it here. In the we call it row reductions. And then after we dive into the determinants, we are having the inverse. Okay? The inverse means that if we can make this this property here, matrix A, matrix B equal matrix B, matrix A equal the matrix identity. we call that this B is the inverse of A. And there is some property that is, I think, important here. And then we have the adjoin method. Okay, adjoin method. So basically, the inverse is we are going to evaluate the determinant and make it into here. 1 of the over determinant of A multiplied with the adjoint A. Basically, adjoint, if we just look at the example here, we are just having switching this A and D, and then the other part is taking by minus. Okay, minus, minus, minus. Like here, maybe we can check here the example. Okay. So we switch this and take minus here. Okay. If we have 3 by 3, we also have the adjoint here. Or if you want to take another approach with determinant, we can also use this method. Basically, you are writing the first and second column in the right side here. So we have five column, and then we are cross multiply and add, and then minus cross multiply and add. Okay. And then it should be the same results with the usual determinants calculations. Okay. Okay, and then row operations. We can also use this row operation to find the inverse. Okay. So we have matrix A. So the idea is this row operations we are going to have. So we have on the left side here, this is the matrix. On the right side, this is the identity. The goal is we want to make the left side, the A, becomes identity. And then whatever happens on the right side here, this will becomes the inverse. So we can use the row operators. So we can subtract, we can add, we can multiply with scalars. Okay. So that's what's happened, and we can. I think it's much more efficient if, but I think it also depends on the numbers and calculations. Sometimes if you see the numbers is, I think if the numbers is quite easily to be add or subtract, I think you can just choose this method. I think it will be going to be faster. Unless there is some parts of numbers that may be difficult to compute, then you can use the just usual the adjoin method. Okay. Like here, example here, idea is from here, from this part, okay, we are going to make it into this part, and we can say that this is the A inverse, okay. And then now I will continue, okay, I will continue with the uh, okay. And then there will be a singular matrix. Okay, I forgot to mention the singular matrix. This is when if we cannot find the inverse. So matrix A, example. If you have this is 1, 2, 6, negative 1, 4, 0, 2, 5, negative 3. has no inverse. Why? If we take this into our forms with the identity, so I make this form, so 1, 0, 0, 0, 1, 1, 0, 0. Okay. Let me make smaller. Okay. Now the idea, as usual, we are going to make this and this 0. Okay. That's the first part. So we can take the R2 minus 2R1, okay, to make this second one. So the first part just write as it is. Okay. And then 2 minus 2 is 0. 4 minus 2 is 6. 5 minus 4 is 9. 0 minus 2 minus 2. 1 minus 0 is 1. 0. Okay. And the third one is the same. Okay. We can do it one more time here. And we want to make the third part or the third row, the 6 becomes 0. So we can take R3 minus 6R1, right? So the same thing we write. This is 0. 0 minus 6, it's 6. Minus 3 minus 12, it's 15. Or 6, right? Minus 6 minus 3, 12. 12 minus 3 is 9. 9. 0 minus 6 minus 6, 0, 1. And we see that we have 6, 9, 6, 9. We can take this and subtract for that row. Let me subtract for the third row, so I will write the same at the second row. And this will be 0, 0, 0. Minus 6 minus 2, it's minus 4, minus 1, and 1. Now we have the 0, 0, 0 here. This is what we call the matrix is singular matrix. So because, let me write, matrix on the left has row of zeros, we can conclusion the matrix is singular. It means that it's not invertible, or we cannot find the inverse. No inverse. Okay. So why this row of zeros makes this no inverse? Because we need this last zero here to be 1, right? That's the goal to find inverse. But if not, then if this is 0, all 0 here, then this is the singular matrix. And sometimes we can use the matrix. Okay? We can use the matrix or the inverse of the matrix, okay, to solve system equations. Okay? So, for example, if usually we write A is a matrix, okay, with a bold A, and then X is also a matrix, okay? And this is equal B. Okay, this is a usual matrix. Okay, matrix. Let me define. Let me define. Let's say A is A11, M by N matrix. Okay? M by N matrix. Let A M by N, and X is from X1 to Xn. So just one column, and B also one column. Okay, so we can write this in a system like this. And remember, if let me write again the equation: A X and then equal B. Remember, in matrix, if you want to multiply the equations with another matrix, for example, if we multiply here C, we need to multiply this is also C on the left. If we multiply on the right C, we will multiply on the right also for the right side. Okay, that's the matrix property. So if we want to multiply, for example, if you want to solve X, we need to multiply the left here with the A inverse. Okay, which means that it will be matrix identity, right? So we are going to multiply also the left of B, okay? And we can write that X is A inverse B. So we can solve for finding the solution for X, okay? So by using the matrix and multiply with the matrix B, we can find solution for X. Okay, so I think I can give you example on how we can take this with solving the system of equations. Okay, wait for a moment if you want to take notes here. Okay, now if we want to solve, let's say we have 2x1 minus 9x2. I will have this variable, okay, x1 and x2, and 3x1 plus 6x2. Okay, we can write 2, -9, 3, 6, and then x1, x2, 15, 16. Now, if you want to try using the inverse, okay, we can try to make the inverse for this inverse here. So we find the determinant first. Determinant will be 12 minus 27 is 39, and it is not equal 0, right? So we can find the inverse. So it's non-singular, so we can find the inverse. So the inverse, we can write the inverse. Usually we can write just adding -1 on the up upper part of the matrix. It means it's not 1 over, it's not reciprocal, it's an inverse in matrix, okay? Because we are in matrix now. So we are going to have 1 over 39. This is 6, 2, negative 3, 9. So this is the inverse, okay? Now we can take, because if you remember that x will be A inverse of B. So the inverse and then multiply with the matrix B. Matrix B, we can find matrix for x. Let me write here that x1, x2 is equal, the inverse here, let me write 6, negative 3, 9, 2, and then multiply with 15 and 16. And we can just multiply as usual with matrix property. So we are going to multiply 6 with 15 and 9 with 16. Let me check. 144 plus 90 is 234, 234. And then the other part is negative 45 and 32. This will be negative 13. Negative 13. And then multiply with 1 over 30, 39, 1 over 39. 39, maybe 39 and 6, right? Same. So 6 and 3. Or this is 1 over 3. So we get that x1 is 6, x2 is negative 1 over 3. So we can find the solutions, okay? And same thing with if you have 3 by 3 matrix, okay? Suppose you are able to find the inverse. Okay. Okay, the last part of this inverse is there also a homogeneous system we can have when we are having the trivial solutions. Okay. But before that, let me write some theorem about the uniqueness. The uniqueness. So when determinant of matrix A is not 0, solution of system AX equal matrix B is unique. Let me write is unique. Okay. Suppose determinant A is not 0 and x1 and x2 are two different solution vectors. Then ax1 equal b and ax2 equal b implies that ax1 equal ax2. Okay. Since A is non-singular, means it has the inverse, then A prime, not A prime, A inverse exists, and so we can write multiply A inverse, and then this is AX1, and also A inverse AX2. And this gives identity matrix X1 and identity matrix X2. Or X1 is equal to X2, which this problem contradicts assumption that X1 and X2 are different solution factors. This is just to give you an idea that if you have the determinant, it's not it's having not zero, it's non-singular, it has a inverse. The solution of the AX equal B will be unique solutions. Okay? And this is just to show you that if we are making this assumption that this x1, x2, two different solution vectors, when we try to look at the using the inverse, it gives us that it's supposed to be the same. Okay, it's supposed to be the same, and then it seems we broke our assumptions, right? So this is just to say that there is only exact x1 or x2 solution. We just pick one, and then that's just our solution, and that is unique solution. Okay. So another way or another perspective is we also have the homogeneous system. Homogeneous system. We can write AX. It's not equal B, so it's just equal 0. 0 means the matrix 0. It's 0 matrix. Okay, homogeneous system. Recall so we have or always possess trivial solution x equals 0. Okay. And possibly an infinite number of solutions. Okay. So a homogeneous system of some n linear equations in n variables, which means we can have 2, 3, 4, and so on. Variables ax equals 0 has only a trivial solution if and only if A is non-singular. So we need to check the determinant A. We need to have the determinant is not 0. Okay. And we can say that when it's non-singular for this homogeneous system, it's only have this trivial solution. Okay, what happens if A is singular, then the AX equals 0 has non-trivial solution. Okay. So let me maybe going for here. Okay. So if A is singular, then AX equals 0 has non-trivial solution. Absolutely, remember trivial and non-trivial. Trivial is making all the things getting a 0. That's trivial. Okay. Now, if we make this, then we can conclude to a conclusion. AX equals 0, the matrix. Okay, this will possess one only trivial solution if and only if determinant A is not 0, and it will have a non-trivial solution if and only if determinant A is 0. So this is the conclusion from the singular or non-singular matrix. And we are going to look on these non-trivial solutions later on in eigenvalue problem. Okay, later. Okay, now I will just review the Cramers rule a little bit. The same thing we've done in the last session, the differential equations, the higher order. We use the Wronskian, right? Wronskian to find the linear independent, and then the Wronskian, we can solve the Wronskian using the Cramers rule to find the u, right? The u inverse, not u inverse, u prime, and then we integrate and we find um, the the multipliers for the first and second solutions in the higher order, right? Okay. Okay, to start with, the Cramer's rule just a set up solutions to solve the system of equation using the determinants. Okay, so let me write here Cramer's rule. This is just a short section, just a reminder. So if we have let me okay, if we have a system of equations that a11 x1 plus a12 x2 equal b1, and then a21 x1 plus a22 x2 is b2. 1 1 1 2, it's just to make this can be written as a matrix. Okay. Now, if we solve this, if we solve this through some substitutions, eliminations, and so on and so forth, we can make the solution for each x1 and x2. We can write and then x2 becomes a11. Okay, what's the deal with this is we are going to have the thing here. This is the determinant of the its matrix, right? The matrix here, determinant, and the upper part is also determinant, but we change with b. Okay, so we can write that x1 is determinant. We have b1 and b2, so b1, b2. So we just change the left part of the matrix with b1 and b2, and this is the total determinants. And for x2, we are going to replace the right side. Okay, and then we need to make sure that the determinants on the bottom part here is not 0. Okay, and this is what we call the Cramers rule. This is as simple as that. Okay. And we have more than two variables, like 3, 4, it means that the solutions also can be depends on how many variables we have. Okay. Yeah, I think that's the Cramer rule. Okay, maybe if you have any questions. So as a reminder, we will have quiz on Laplace, maybe this week. Okay, this week. Maybe from tomorrow. Maybe just having 4 days, okay. And then the lecture we focus. Today I will finish this matrix, okay, and then we are going to have another section, another chapter, which is the vector calculus. Okay. Probably at the end of the lecture for this morning, I will give you some feedbacks. I would like to know the Laplace. Okay, so I will give you some question on Laplace. And the afternoon session, I think we can focus more to the vector calculus. So I will start now the after this Cramers rule, is the eigenvalue, eigenvectors. Okay, wait. Okay. Okay, okay, we can start. Okay, now we move to the eigenvalue problem. We call it eigenvalue problem. We will start with definitions, okay, to give you what we are doing here. Okay, what we are doing here. So definition. So let's define A as a matrix, okay, n by n matrix. It should be having the same row and column. A number to let's say we have lambda. We have a lambda is said to be an eigenvalue. Okay, we develop a new terms here, eigenvalue. Eigenvalue of matrix A. Matrix A. If there exists a non-zero solutions, which means the non-trivial we have before, the non-trivial solutions, factor k, okay, of linear system. And we can write that it's a k equal lambda k. Sometimes in your textbook it can be k, it can be x. Sometimes we call also this k is like a factor. It's a factor solutions. So we can also call this with factor x like that. But it's the same meaning. The same meaning. It's a solution factor. Okay, now this k, this is we call the eigenvectors. Eigenvectors corresponding to the eigenvalue. So this is eigenvalue, and that is eigenvectors. So what is eigenvalue means? So eigenvalue in terminology, in language, means that it has characteristic value or characteristic factors. And we can find the eigenvectors using the Gauss-Jordan eliminations, the one we have before with row operators. Remember, we have to find our goals, find 1 1 1 in the diagonal. That way we can find the eigenvectors. Okay, let me give you some example first. First is verify. So let k, the factors, is having 1, negative 1 1, and we have a 3 by 3 matrix, 0. Okay. Okay. Let's say we are multiplying this A and K, both matrix together. Can we multiply? 0, 1, 0, minus 1, minus 1, 1, 1 minus 3, it's minus 2, right? Minus 2 on the top. The second row, 2 minus 3, it's minus 1, plus 3, it's 2. The third row, minus 2, minus 1, minus 3, plus 1 is minus 2. Okay. And then see, we can factor 2 out, or rather we can factor negative 2. And we can have this 1, negative 1, and 1. Now, we call from this K and A, we call that this negative 2 is our eigenvalue. And then we can write the property to solve this matrix algebra. We can write that A minus lambda identity multiplied with K is supposed to be 0. And then eigenvalue is sometimes it's not only one value. Okay, so let me write here. Matrix. A matrix can have multiple eigenvalues, but no more than its number of rows or column. So it's not exceeded the number of rows or columns. Okay, and then let me write again this part. So A minus using with white, A minus lambda identity, and then K is 0. Okay. So since this, if we break down this and make it into like a homogeneous system, right? We would like to find, we seek the non-trivial solutions, right? We seek only the non-trivial solution. So remember, what is the when we have non-trivial solution, what should we have? Let me go back and then here. The non-trivial solutions if determinant is 0. So that's what we are going to apply. So we apply here that the determinant of A minus lambda identity, this should be 0. So this is an implications that we need to find the non-trivial solution. Okay. We call this determinant later on. We see that it will be it's like an equation because we have the lambda inside, that the lambda that we want to solve. Okay, we may have some polynomials happening in this determinant. So we call this characteristic equations. Characteristic equation of A. So the eigenvalues are basically roots of this. And then after we find the eigenvalues, eigenvectors can be obtained by solving system of equations and then use the Gauss-Jordan elimination. Okay, maybe I will give you some logic behind why we need to have this determinant equal 0. Okay, let me give you some logic. Okay, so if we take the first definitions of the eigenvalues and eigenvectors, if we have this, let me write some arrow here to just to make sure that this is eigenvectors, not another matrix. Okay. Okay. Now let's move this to the left side. Okay. This is at 0 factors, and we take this. Okay. And then we also take some identity here, so we have our same formulations there. Okay. And then this part, we say that it cannot be 0, right? Okay, now take the inverse. So the inverse on the left, so A minus lambda identity inverse. If we multiply, and then we take also the inverse here and multiply with the 0 factors. So we will have K is A minus inverse 0 factor. So K is 0, right? But we don't want to have this happen. Okay, we want to avoid this. So our conclusions that this not A, sorry, lambda cannot be invertible, which means that we don't want this to be invertible. So we are going to, so this part should not have any inverse. Okay. So if we take that as our definitions, then this will have the determinant is 0. Okay. That's why. So that we don't have any inverse. So that we are going to have this as our characteristic. Okay. Okay. So let me give you an example on what steps do we need to take for finding these eigenvalues and eigenvectors. So let me show you. Well, let me give you an example. Okay, let's say we have matrix A. Let's start with 2 by 2 matrix. Okay. The first step is we are going to find the lambda by taking this matrix A minus lambda. Okay. So we will have, let me just write one by one so that you know what is happening here. This is matrix identity. So we are going to have 1 minus lambda, 1, 4, and 1 minus lambda. Let me make this a little bit closer there, closer, closer there. Okay, so we have this. So we need to set the determinant of A and lambda identity is supposed to be 0. So by doing this, we're going to have that is determinant is going to be 0. So we are going to have 1 minus lambda squared minus 4 is equal to 0. Now this is what we call the characteristic equation, like we defined as the previous page. Okay. So characteristic equation. Okay. And we simply solve polynomials and finding roots. Okay, that's basically what we are going to do more and more later on. Okay, so we are going to have lambda squared minus 2 lambda plus 1 plus 1, so minus 3. Okay, this equals 0. Now we have lambda minus 3 and lambda plus 1. So we can say lambda 1 is 3, lambda 2 is negative 1. And we have 2 eigenvalues, so this is eigenvalues. And how to solve now finding the eigenvectors. Okay. Well, let me give you a question here. Find eigenvalues and eigenvectors. Okay. Now how to find the eigenvectors? Now we simply set is A. Let me write again. A is 1, 1, 4, 1. And we have eigenvalues equal 3, eigenvalues equal negative 1. Right? Now for eigenvalues equal 3, we are going to have A minus 3 identity. So 1, 4, 1, 1 minus 3, 3, 0, 0. This will be negative 2, 4, 1, negative 2. Okay. Now this is should be equal to 0, 0. And we need to find the echelon form using row echelon form. Solve this using, or we can just find Gauss-Jordan or row echelon form. If we look here, the first row is simply half of the second row, multiplied with negative, of course. So we can take this and solve through the echelon form. So we can write negative 2, 1, and 0. Yeah, we can just I think we can just take this as using the directly row echelon here. Okay. So let me multiply the first row with 2 and then adding with the second row. So 4 minus 4. So 4 plus minus 4 is 0. Negative 2 plus 2 is 0. So it's, we have this 0, 0, 0. We call this the infinitely many solutions, right? So basically we say that in here we got negative 2x1 plus x2 is 0. So x1 or x2 here is 2x1. If we let x1 is 1, so x2 is 2. So we can choose our eigenvectors. We can choose eigenvectors here to be 1 and 2. And any multiplication of these vectors also works. So we could also say that eigenvectors, we can use C or K. It's also okay. Okay. But we can just write just this. It's also okay. You can choose the C is just 1 and then it will be 1, 2. That's for our eigenvectors. That is for eigenvalues equal 3. Now we should also calculate the eigenvalues equal negative 1. So let me move to the next page to see that we have 4 eigenvalues negative 1. So we'll have a minus 1 and then identity. So let me write 1, 4, 1, 1 minus, this is minus 1, 0, 0, minus 1. So we have 2, 1, 4, and 1, 2. Okay. And the same, we are going to have the row echelon form. And if you see, it's just twice the row. The first row is half of the second row. So we can write 2, 1, 0. And then 4 minus 4 is 0, 0, 0. And we see that this becomes 2x1 plus x2. So x2 is negative 2x1. So if we let x1 is 1, x2 is negative 2. So the factors, the eigenvectors is 1, negative 2. Okay. So maybe this is K2, this is K1. Okay. To make it easy to distinguish. Okay, let me give you another example. This is 2 by 2 matrix. Maybe it's too simple. Let me give you. So if let me go give you 3 by 3 matrix 1, 2, 1, 6, or let me give you the easiest one to solve first. Let me just give you 0, 0, and 3, negative 2, 0, 2, 3, 4. Now find eigenvalues and eigenvectors. Okay, so always start with, let me give you step step-by-step here. Always start with the matrix minus lambda identity. And then we start with matrix A minus lambda identity is equal. It's simply just take the diagonal, right? The identity is just diagonal, right? So 1 minus lambda, 0, 0, 3, minus 2 minus lambda, 0, 2, 3, and then 4 minus lambda, right? So always start with this. Okay? Now the second step is take the determinant of A and take this as 0. Okay? Okay, since I make this matrix having 0, 0 here at the upper part, so it will be easy to find the determinant, right? We can just focus on this one here. So the determinant will be equal to 1 minus lambda multiply with determinant of -2 negative lambda 0 and then 3 4 minus lambda. So we can multiply 1 minus lambda and multiplications of -2 negative lambda and 4 minus lambda is equal to 0. So we don't need to multiply at all. We already have this as solutions, right? So the first eigenvalue, so 1 minus lambda is 0. So lambda will be 1. So let's say lambda eigenvalue 1. The second one, so eigenvalue 2 is -2. And the third one, 4 minus lambda is 0. So lambda 3 or eigenvalue 3 is 4. So we have these three eigenvalues. Okay. Okay. Now to find the eigenvectors, let me put an example here. Okay, let me move to the next page. So to find the eigenvector, so the next step, let me write, this is step 1, step 2, step 3. Check each eigenvalues. Maybe not check. Put eigenvalues in a, okay, or maybe directly, and solve with Gauss-Jordan elimination. Gauss-Jordan or row echelon form. Row echelon form. Okay. So for example, we take the eigenvalue equal 1. Okay. So this means that this is A minus 1, right? And the identity. So this is just to write 1, 0, 0. This is A. This is minus 1, 1, 1. This becomes 0, 0, 0, 3, -3, 0, and 2, 3, 3. Okay. We can take this directly to 0, 0, 0. And since we already have the first row is all 0, I think we can take the conclusions. that if we take this, the second row, we can say that 3x1 minus 3x2 is 0. So we can say that x1 is equal x2. And then the third row, we can write 2x1 plus 3x2 plus 3x3 equals 0. If we let this equal 1, okay, so we are having 2 plus 3 plus 3x3 equals 0. So 3x3 is equal to negative 5, or x3 is negative 5 over 3. So we can write that x, or maybe k1, we can write this as 1, 1, negative 5 over 3. We can choose, okay, we can choose this. If we let this equal 1, x1, x2 equal 1. Now the second eigenvalue is negative 2. So we are going to have a minus minus 2 identity. We can, I will write directly just plus 2. So I will plus all this 1, negative 2, 4 with 2. So I will plus 2. So we will have this as 0. So this will be 3, 3, 3, 2, 0, 0, 3, 0, 0, 6. Okay, I will directly write like that. We say that 3x1 is 0, or let me write with the 0, 0, 0, forgot to put here. Okay. So 3x1 is 0, so x1 is 0. x2 is also 0. So 2x1 plus 3x2 plus 6x3 equals 0. Well, x1 and x2, we need to just to have one, so the other one is not yet confirmed. So we can just write, let just this x1 first, okay, to make it 0 here. So we will have 3x2 equals 6x3. So x2 is negative 2x3. So if x3 is 1, so x2 is negative 2. So we can have our k2. This is 0, negative 2, and 1.
0 minus 2 is negative 2.
Okay. Now the last one, the eigenvalue equal 4. So a minus 4 identity. So 3 or is equal 1 minus 4 is minus 3, 3, 2, 0, 0, 0, negative 2, negative 4, negative 6, 3, 0. Okay. I'll start with the solving row echelon, just writing here, just to know that this we are doing the row echelons. So negative 3, x1 is 0. So x1 is 0. So 3x1 minus 6x2. So 3x1 is equal 6x2, or x1 is equal 2x2. But since x1 is 0, so x2 is also 0. And then for 2x 2x1 plus 3x2. It's the same thing, right? Okay. So since we can write since x3 is since x3 is having all zero, so we can say that x3 is free variable. So we can let x3 equal 1. Okay, we can just let equal 1. So our eigenvectors, the third one, or let me write maybe using white color. So the third eigenvectors is 0, 0, and 1. Okay. Okay, and then we got all the eigenvectors. Okay. Eigenvectors 1, 2, and 3. Okay. Okay. Maybe if you have any questions first. Do you have any questions? Okay. Okay. If not, then um, okay, we can continue. Continue to the sections that the eigenvalues may have a complex eigenvalues. So matrix A, may have complex eigenvalues. Okay. So let A be a square matrix. Square means the same row and column. And if we define the lambda with alpha and some beta with complex imaginary here, and beta is not 0, this is we call the complex of eigenvalues of matrix A. Then the conjugate, we can write the conjugate is same lambda but with some line in here. We can say this is the conjugate. The alpha minus imaginary beta is also eigenvalue of A. And then if the eigenvector K is eigenvector correspond to lambda, then the conjugate K, and with line here just to make the notations to be obvious with the lambda. So we can say that this is eigenvector to the lambda conjugate. Which means that why we have the complex may comes from the characteristic equations. When we deal with the roots, finding the roots of the characteristic equations, maybe the roots itself is not a real root, so it may have the imaginary number. Okay. So if we decide, so example, the matrix A 6, 5, -1, 4. Okay. If we want to find the eigenvalue and eigenvector, let's say we are going to find the determinant first. So we will have 6 minus lambda. Okay. Now we can calculate. So 6 minus lambda, 4 minus lambda, minus 5. So we will have lambda squared minus 10 lambda plus 24 plus 5 is, or plus 24, oh this is plus, sorry, plus 24 plus 5, so plus 29. So this is our characteristic equation. Okay, now we know that this will resulting the complex. So we need to solve this, finding the roots. So the roots we can find through we can make it complete standard form, or you can just always using the ABC formula, the quadratic formula. But let me just write with this is lambda squared minus 10 lambda. It should be plus 25, right? Plus 4. This is lambda minus 5 squared plus 4, right? Okay, now this we have lambda equal negative 4. So lambda minus 5 is square root of negative 4 is 2i, right? Plus minus. So lambda 1 is 5 plus 2i. Or maybe we set the lambda with the line here to make the conjugate. The second one is 5 minus 2i. Okay. Okay. And then we can use this to take solving the eigenvectors. So lambda is 5 plus 2i. So a minus lambda, right? A minus lambda is 6, 5, 4. This is 5 plus 2i. Six minus 5 is 1 minus 2i, right? This is negative 1, 5, 4 minus 5 is negative 1, negative 2i. Maybe let me write here to make so we don't confuse with the right part. Okay, so this is we solve through the row echelon form. Okay, so we have x2 is 1 minus 2i x1, right? And 5x1 minus 1 minus 2i, or maybe that x2 is 0. So we can see from here that x2 is this. So if we let if x1 is 1, then we can set the k1 is 1 and 1 negative 2i. And the same thing if we're done with the conjugate. If we're done with the conjugate, we are getting the same or similar connections. Then if we try to make it through here, a minus 5 plus 2i, okay, this will be equal to sorry, not 5 plus, but 5 minus. So 6 minus 5 is 1, 0 minus minus plus 2 plus 2i, negative 1, 5. 4 minus 5 is negative 1 plus 2i. I think it's similar, but if you look at here, it's precisely what we have in the conjugations. It's going to be having the opposite signs. So this will result in the other. So k2 we can say it's going to be, or let me write with the green color. Look at the k1 is 1 and 1 negative 2i. We have k2 if you compute this and see the row echelon form, and if you let uh, one of the solution is 1, then you will see that the same or similar structures. Now this we can call this part is just the k1 with the conjugate there. So which means actually k2 and k1 has the same structure. Y negative 5. Negative 5 is from where, Doron?
It's before, sir. Oh, it's the previous page before.
This, which one?
Oh, you corrected already before.
Oh, already? Okay,
Yeah.
okay. Okay, now when we have the complex or we have the eigenvalues that has conjugate, the result for the eigenvectors, it will also have the conjugate. So if we have the first one here is 1 minus 2i, then the other form, the other eigenvector will be also having one something here. The something here that it has the complex will be the conjugate of the first one here. Okay, so you don't really need to calculate or prove this part and make it into the to find the eigenvectors. You can simply look at the first eigenvectors here, and then you can simply write, oh, the second eigenvector should be equal. It should be having the similar structure. So 1, but instead of the 1 minus 2i, it has the conjugate, which is 1 plus 2i. Okay. Okay, there will be some, I think, 2 or 3 sections and theorem. Let me check. Well, if we learn eigenvalue, eigenvectors, ideally we need also to learn the diagonalization. But for our course, this summer course, I will just take the matrix until the eigenvalue and eigenvectors. Okay, so I will not going to further into the orthogonal matrix and diagonalizations. Well, it's supposed to have that, but I will just skip the last part. Okay. Okay. All right. Okay. This is we call the eigenvalues and singular matrix. Okay. If number 0 is eigenvalue of n by n matrix, matrix A. Okay. Then, by definitions, this is the lambda here. Okay. The lambda is 0. So by definition, this should be a 0, 0, 0 factors or 0 matrix. Okay. So the homogeneous linear system of n equations in n variables must possess non-trivial solution of K. Okay. We know this from before, right? So from here, from this fact, from this definitions, this tells us that there is something important on the matrix A. So we say that when we have the homogeneous system for n equation in n variables, they will possess a non-trivial solution if the coefficient matrix is singular, right? The coefficient matrix is singular. Matrix A is singular. Okay, so we may say that if we let A be n by n matrix, then if lambda is 0, if lambda 0 is an eigenvalue of matrix A, or maybe not if, this should be lambda 0 is an eigenvalue of A if and only if A is singular. So we need to make sure that A is singular, then we say that lambda equals 0 is the eigenvalue of A. Or in a different way, we can also say that matrix A is a non-singular if and only if the number 0 is not an eigenvalue of A. So how to find the singular or non-singular? We find through the determinants. Okay, the determinants. So determinants, if this is not 0, then we call this non-singular. When determinant A is 0, it's singular. Remember at the beginning of our definition on eigenvalues and eigenvectors, we need to make sure that the determinant is equal to the 0. It should be singular, so that we can calculate, we can compute. Okay. And then again, I will going to include the inverse, like we made some logic before. Okay, so let me write again the inverse. So if we have a k and then lambda k, right? So multiply both sides with a inverse from the left. Okay. So this is a inverse a k. Since eigenvalue is just a scalar, I will write eigenvalue here to see, so directly we can write here like this. So this will be identity k, and then this will be lambda a inverse and k. And we can say that this a inverse k is equal, since lambda is just a scalar, we can move and divide with lambda, so we can write 1 over lambda and k. So we can make some conclusion from here that if you let A be a non-singular matrix, if lambda is eigen, let me write with a different color. Eigenvalue of A with corresponding eigenvector k, then 1 over lambda is an eigenvalue of A inverse. Okay. With the same corresponding eigenvector k. If you see here, there's nothing change this k here, but we see that when it becomes A inverse, it's become 1 over lambda. When it's just A, it's just lambda, but when we have A inverse, it becomes 1 over lambda. So before, at the beginning, we say that we don't want the determinant to be non-zero, but now we can have some situation that have that the matrix has the inverse. Okay. Okay, let me give you some sort of example, just a simple verifications. Okay. So example. So let's say matrix A is 4, 2, 0, 3. Let's say it has distinct eigenvalues. Yeah, let's say we have its eigenvalues. We have the eigenvectors. Since we say 0 is not an eigenvalue of A, then we say it is non-singular. We can say that we will have the reciprocal, the third eigenvalue, which is 1 over lambda 1, which is 1 over 4, and the second eigenvalue, which is 1 over lambda 2, or 1 over 3. So we say that the lambda 3 and lambda 4 is both are eigenvalues of A inverse, with K1 the same thing and K2 also the same. Okay. We can verify it easily using A inverse. We can take this 1 over 12, 3, 4, negative 2, 0. Or we say that this is 1 over 4 and 1 over 3, negative 1 over 6, and 0. So we can compute the A inverse with K1. So 1 over 4, negative 1 over 6, 0, 1 over 3. This is 1, 2. So we will have 1 over 4 on the top, and on the bottom 2 over 3, 4 minus 1, it's 1, 3 over 6, so it's 1 over 2. Now we can factor out 1 over 4, and it will be resulting the eigenvalues 1 over 4 are the same, and eigenvectors of K1 here, right? This is just to verify whether our theory is correct or not. Okay, and then the second, we can check the A inverse with the K2. Okay, there's 0 and 1. This will be 0, and the other part will be 1 over 3. So we can factor out 1 over 3. And we know that this is the lambda 4, right? Lambda 4, 1 over 3. And this is the K2. Okay. So we are able to verify that it is true that when we have this, the matrix A is non-singular, we might have the inverse, and we can also verify its eigenvalues of that inverse of matrix. Okay. And notice that from what we learned, okay, when we have this matrix, see that the pattern, okay, see the diagonal here. This is maybe becoming important, okay. It's 4, 3, 4, 3, okay. And when we have the inverse is 1 over 4, 1 over 3, 1 over 4, 1 over 3. So the diagonal becomes our key, okay, key point. So it's become another theorem in the eigenvalue and eigenvector. We call it triangular and diagonal matrix theorem. So eigenvalues of an upper triangular, lower triangular. This is lower triangular. We have 0 here, right? And diagonal matrix are the main diagonal entries. So when we have A, 4, 3, so it means that this is lower triangular, okay? So we say that the eigenvalues is this. This is eigenvalues 1, eigenvalues 2. Okay. Okay, any questions?
Hello.
Yes.
Oh, can I ask like
Yeah, yeah.
from from the previous page, like when the eigenvalues minus where is that? Previous page again.
Mm-hmm.
Yeah, that one. The bottom part.
Mm-hmm.
Yes, that one. A minus two A minus on the left side.
Mm-hmm.
Yeah,
This
that,
one.
yes, that one. Like when we minus A minus eigenvalues, do we
Mm-hmm.
get like always that 0, 0 on the right side?
Yeah,
Is
always,
it also?
always, always.
Okay. Oh, that's like I'm confused. Like where can we get that? Okay.
That is from
Yep.
here actually. The where did this is from here. We need to make the determinant is equal 0.
Oh, okay. 0. Okay. Okay. Thank you, Pao.
And then solving the here from here. Actually here from here. Okay. We need to make it 0. Yeah, the very first part here. The eigenvector can be obtained by solving system of equations. This equation is equal to 0. So that's 0 is 0, 0. It means 0 factors or 0 matrix, which means it depends on how many columns or row you have. So if you have 3 by 3, which means it will be a 3, right? 3 rows. Or if you have 2 by 2, it will be 2 rows. Okay.
Also, like it's every time, even though 3 by 3 or 2 by 2, always 0, 0, 0, right? zero
yeah,
zero
it's
and
always
equals.
zero. Yeah, zero. It will be fitted with your number of row and column. Okay. Okay. Previously I mentioned that we might not have diagonalizations, but I think we can have just a small parts of the diagonalizations. Okay. So I will just write like a really short summary on how we are going to at least apply this diagonalizations. Okay, we call it diagonalizations using the eigenvalues and eigenvectors. So actually the part in matrix is it has a lot of parts, but I skip a lot. I skip the power of matrix, the rank of matrix, the orthogonal matrix approximations. The, there is some application for cryptography, the error correcting, and discrete compart. So I will skip all that much. At least I will just give you the the most important thing is the aside from determinants, inverse, Cramers rule, the eigenvalues, eigenvectors, and the applications, which is the diagonalization. So this will be the application. So I think I will just focus diagonalizations, just a small part, and maybe continue a little bit on the afternoon sessions, and then we move to vector calculus. Okay. So diagonalization, we can say that this will be an application for uh, eigenvalues and eigenvectors. So by definitions, the diagonalizations is we can call. I think I will just give you the important part. Okay, let me check your textbook first. Okay, the question is actually for, let's say, n by n matrix A, can we find n by n matrix B for we have A, P, P inverse equal the diagonal. This is what we are usually taking. Okay, so we are going to find this D. The D is means the diagonal matrix. Okay. Okay, maybe we can start with. Okay. Okay. So let me write that diagonalization involves taking a matrix and write it as a product of matrix. Okay, to get into what we have here, the P, okay. Let me consider not P, but maybe just X, okay, to give you more idea here. So consider if we have A equal X diagonal and X inverse. So we have this matrix, okay. So first, we want to multiply on the left with the X inverse. And then multiply on the right with X, okay. So we are going to have X inverse A. X is our diagonal. Okay, this is perfectly what we have here, similar structure. And since we have A here, the D on the right side, this will made up by eigenvalues of A. Okay, why I take this as important note, if we remember that we have this connections here, the diagonal is our eigenvalues, right? So we take this and we write the X matrix is said to be, or is said to diagonalize A, okay? And we said that the A has unique eigenvalues to make this happen. And A can have multiple eigenvalues if they have linearly independent eigenvectors. This is we call this sufficient conditions conditions for, let me write here, condition for diagonalizability, okay. Ability to diagonalize. So we can say that D is made of eigenvalues A. And X is made of eigenvectors A. Well, you can say it's X or K, using the same K as eigenvectors is, I think, also fine, because I think your textbook using with K, so I think let me just write this with K to make it similar with the textbook. But let me just write this X is and A is just as it is. But let me just write K here is made, or X here made of eigenvectors A. Okay. Okay, now I will make some steps, okay, to see how we are going to diagonalize a matrix, okay. but first, let me give you some notes. So assume n by n matrix with eigenvalues. Let's say lambda 1, 2, until some lambda n. We say that the diagonal is okay. So if k1, k2, and kn are eigenvectors of A, then the k that we want to apply is k1, k2, until kn. Okay. So another thing that we need to set up is we need to set the d and k with orders. So we need to arrange. Okay. Okay, let's say we have matrix A. Okay. First thing, if you want to diagonalize, we need to, of course, evaluate eigenvalues, eigenvectors. Okay. Okay. Now to find the eigen, so first step 1, find lambda or eigenvalues. So step 1 is finding the determinant of A minus lambda is 0. Okay, and then
Get that.
minus 3 minus lambda 5 negative 4 6 minus lambda
546 minus 1 is 545.
minus 20. Okay. Okay. Now we have lambda squared, negative 6 lambda plus 3, so negative 3 lambda. Negative 18 plus 20 is plus 2. So we will have negative lambda minus 2, lambda minus 1. So lambda 1 is 1, lambda 2 is 2. Step 2, find k or eigenvectors. This is as usual as we did before. Okay. So we take this into, so let me just remind you why we have 0 on the right side. This is because a minus lambda I and then multiply with the eigenvectors is equal to 0. Okay. So we are able to find, first is using 1, eigenvalue is 1. So this will be negative 3, negative 1, so it's negative 4, negative 4, 5, 6 minus 1 is 5. And then we are going to use row echelon form using the 0, 0 here. Okay. And then from here, it seems that we get this. Okay. And either you check with first row or second row, you have the same conclusion. So we say that the k1 is -1, 1. So let x2 is equal 1, right? Okay. And then for the lambda 2 is 2. This will be 5, -4, 5, 4. Okay, take the row echelon form. And we can see that from here, we see that this is -4/5 x2. So if you let x2 is equal 1, so we can get the eigenvectors. It's -4/5 and 1. Okay, so we have this eigenvectors. We have the eigenvalues, right, from the previous one. So we are going to perform our diagonalizations. Okay. Okay, let me write step 3 on the next page. So step 1, step 2, step 3 is perform diagonalizations. Diagonalization. Okay. First, we are going to write our D as using the eigenvalues. We are writing from the lowest to highest, so 1 and 2, okay? And we are writing the K. We're writing and making this 1 here at the bottom. So why we need to take this? Actually, we can take x2 as any constant, but we just need to take this equal 1. Okay, so we write -1 and 1, and -4/5 with 1. This is correspond with this, right? And this is correspond with this, okay? Okay. Now first is finding the K inverse. The K inverse, maybe finding the determinant K. Determinant is -1 plus 4/5. It's -1/5. So 1 over determinant K is -5. Okay. So the K inverse is 1 over determinant K, and then this will be 1, -1, -1, 4/5. Or this will be -5 multiplied with all this. Okay, that's our inverse, K inverse. So all components completed, then we can confirm that this should be K. So we can verify that A is K, B, K inverse. So we can verify with our K is -1, 1, -4/5, 1, and then D is 1, 0, 0, 2, and then this is the inverse. This is negative 1. This is negative 8 over 5. 1, 2. And doing one more. Multiply. 5 minus 8 is negative 3. Negative 5 plus 10 is 5. 4 minus 8 is minus 4. Minus 4 plus 10 is 6. And this is precisely the a that we have at the beginning, right? So it means that the diagonal is d equal 1, 0, 2 is diagonalizations or diagonal of a. Or if you would like to try from if you want to try from the, I think we can also try from here to take this a and k supposed to be d. Okay. We can also try from here, and we get the same d as we have here, and it is also can be verified, can be proved that this is the same. Okay. So my idea here, or my tips, okay, my tips, maybe I will write here the tips. The tips here always make this one. Okay, this is also make this one, which means that the x2 or the x that is going to be the lowest part, you should let them as equal 1. Okay, and then you need to perform that the eigenvalues need to be arranged from the lowest to the highest. It's my tips. Okay, and then you can directly get the d. Okay, and this is just to verify this, just to verify. This is also to verify that our calculations for d is correct. Okay, so I think that's it just for the diagonalization. Okay, and also this is come from k1, come from k2. That's it. The rest, I think I will just give you as a maybe homework, and then maybe if we still have time, we can have some practice. But I don't think we can have that practice yet, because I need to move on to the next section, which is the vector calculus, and I'm not sure how much vector calculus we need to include into the final exam. I think just the half part of the line integrals, the surface integrals, just a small part. I think that will be enough for our exam. Okay, so I think I will just stop until here, and I will give you the feedbacks. Okay, feedbacks. So maybe before we start feedbacks, any questions? Any questions? And the feedbacks is going to be about Laplace. Okay, so I'm just going to see whether you still remember the Laplace. So if you have the notes on Laplace, maybe you can prepare the notes, and we can play the games for this Laplace. Okay. Okay, I will stop the sharing. I stop the sharing, and I will give you the Laplace. Okay, please join the comprehension. It is about Laplace, most of Laplace. I think Laplace inverse until the convolutions. Okay. Okay, I will wait for a few minutes and then we can start. So the matrix, the diagonalization is just the basic diagonalizations, okay, just to see what is the applications for the eigenvalues and eigenvectors using the to find the diagonal. Okay. Okay, now let's start. Okay, 3 questions in total. Please use your student ID. Okay, student ID. All right. Okay, 3, 2, 1. Let's start the first question. Okay, if you still remember the Laplace, first thing is to see the functions first. And the function is having two piecewise conditions, right? Piecewise conditions. So first, probably using the Heaviside function, right? Heaviside function. So we'll have some translations here, and you will notice that the Laplace transform having the e with power of some bs. Bs maybe is, if you remember, the form is usually having e with power of negative as, right? So probably that is some clue on how we are going to solve this. So first is try to make the functions first. Try to make the function, and maybe it has the Heaviside. Maybe it has the Heaviside function. Around 1 minute 30 seconds. Okay, 21. Yeah, 20 seconds. Okay. Okay. All right. Okay, please let me know who is the cake and Agent X9. Okay, this you can chat in the. Okay, time is cake. Who is Agent X9? Let me know your student ID. Okay. The next question, the second questions. Get ready. Okay, we have Laplace, and then we have t cubed with e power of t, and the question is a is equal to, so we need to find what is a. Okay. Of course, it's a constant, but how to find it that constant? We have around 2 minutes. If you do this, and if you remember, whenever we have the t squared, t cubed, probably it's about translation, or maybe it's about, maybe you could just think from the cube and then the 4 power in the bottom part of the result. Okay, what does it mean? Okay, what does it mean? Okay, 22, 21. Okay, 9, 8, 3, 2. Okay, everyone has voted. Okay, good, good. So it should be 6. So basically you are going to derive three times, right? 3 times. Okay. Okay. So Agent X9, if you can change your name, you can change with your student ID, or you can just let me know what's your name, what's your student ID in the chat box. Okay. Okay. The third question. Get ready. 3, 2, 1. Okay. Oh, Agent. Oh, 041. Okay. Okay. The convolutions. Remember, whenever you have the convolutions, first thing is what is the definition of convolutions, and when you have the Laplace, what is the implication of the convolution? So by now you can check your notes, the definition of convolutions and the implications of what it is if you are transforming using Laplace. Okay, 32, 31, 30, okay. Okay, 12, 11, okay, 9, okay. I think everyone voted. Okay. Okay, good, good. The Laplace of the convolutions means you can separate the Laplace and just multiply. So Laplace, if you have Laplace A convolution B means Laplace A multiplied with Laplace B, okay? Okay, so good. Okay, so congratulations, you win the game. And hopefully today's lecture can be benefits. And as I mentioned, yeah, you can write your feedbacks if you want to write also about your midterm, what's your feeling. I will have another survey of your midterm in the afternoon session later, okay? Why my number is not in Menti? Uh, okay, but I think if you write here, so I know that you are here. So this is just to clarify that this is, I will going to be include this into your grading, okay? Okay, so thank you for your participations and see you in the afternoon session, okay? Okay, so I will stop sharing, okay, and see you in the afternoon session. So thank you very much for this lecture morning session, okay?